Well, welcome back, ladies and gentlemen. Today we're going to talk about 13.2, area of regular polygons and circles. We've done a lot of work in our recent past with trigonometry and the basic area formulas for triangles and quadrilaterals. So it's now time to expand our world a little bit into more complicated shapes like this polygon. Now, the reason that geometry spends so much time dealing with triangles is basically every more complicated shape is just a whole bunch of triangles stuck together. So here is a polygon, and we are only going to concern ourselves with the area of regular polygons in this course. But there's a little bit of vocab we got to go into right here on our note guide right there. And you should have a green resource page that looks a little something like this. And there's some stuff there, but go all the way down to the bottom. Let's talk about polygons here. And we got to fill in a few things. So go ahead and grab your green sheet. Draw this little pizza slice right here, and then draw yourself what's called an altitude, which is just a perfectly perpendicular line like that that perfectly bisects that side length. It doesn't look like it in my drawing, but we're just going to go with it. There are a few words we got to know. We usually think of the word radius associated with circles, but if I extend from the center, oh, by the way, this is a center, that makes sense. Center of the polygon. All right, center of the polygon to a corner of the polygon or a vertex of the polygon. So we got these things. Any point like that is called a vertex. And if you make it plural, it's vertices. I think we've talked about that word, but just to be safe, I'm going to put it there. We got a vertex, and then we got a side. That shouldn't be too difficult to understand. But the new one is going to be, well, there's a couple new ones, okay? So let's talk about this pink angle right there. I think we've talked about this before. This is called a central angle. If we haven't talked about it before, we're talking about it now. That's a central angle. And then I'm going to refer to some of our work right here where we're just going to talk about that angle right there, which is half of a central angle. 1/2 central angle. And basically, those angles are important because, like, for instance, this is a hexagon. This has 6 sides. The central angle, to go fully around, we'd need 360 degrees. But because this is a 6-sided figure, it also has 6 corners. So that means that each pizza slice is worth 360 divided by 6. The half central angle is where things start becoming useful, though, because you notice that I turned that pizza slice into 2 right triangles. So basically everything that we've learned about right triangles applies. Pythagorean theorem, trig, those Pythagorean triples, all that fun stuff, our special right triangles, all that. There is one more word, super important, and will be new. This length right here, apothem. A-P-O-T-H-E-M. Apothem. Just think Mike Tyson trying to say opossum. And basically that is a line that is extended from the center to the midpoint of a side. Okay, so inside this triangle of interest here, we've got basically a pizza slice, and then we chop that pizza slice in half to talk about a single right triangle. And within that, we're no longer talking about the side length, but we are also talking about a half side length right there, going from there to there. And that's where we're going to focus our attention. Basically, what we're going to do is we're going to find the area of one of these little half triangles. Okay, so the smallest slice that you see there. And then we're going to multiply it to get full coverage on the whole polygon. So let's go back to our notes here today. Here we have a nonagon, right? We got, or how many sides does this thing have? Doesn't tell us. Oh my gosh. Okay, well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decagon. All right. Get rid of those marks. All right. We're going to use a decagon for this number of sides. 10. That's a decagon. Triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon. There's, just call it an 11gon. There's a really weird word for it, but dodecagon, and then maybe icosagon, 20 sides way up there. So that was 3 through 12, and then to 20. Know those words. I know I've given them to you in the past. those vocab words are reasonably important, okay? Because I can just say, go find the area of a regular decagon with a side length of 9, and that's basically the same problem as that we have right here. So the way we get started on one of these problems is we just draw the center as best we can, pick a spot. We're going to draw, I'm just going to draw the half triangle. So I'm going to draw a right triangle, and this is going to be our apothem, and this is our radius. And that would mean that our little half side length right here would be 4.5. And you can see that we know a little bit about this triangle. We've got a right angle. We have one side length, but we're going to need at least one more piece of information if we need to, in order to find the area of this triangle, we need the base and the height. So the apothem is going to serve as our height, but we don't know that distance yet. So the key to unlocking this whole thing is to deal with this angle right there. And that angle, if you remember, from our drawing previously, like if I were to extend this out, that pizza slice right there, that's twice as big as the slice I just drew in purple. Okay, so the pink is twice as big. That pink slice covers this entire side, of which there are 10 in this shape, which means this central angle right there should be an even division of 360 by 10 sides. So to find that central angle, what we're going to do is we're going to take 360, and since this is half of that full pizza slice, we're going to not divide by 10, we're going to divide by twice the number of sides. So I'm going to go divide by 20. So to find your half central angle always, it will always be 360 divided by, and I'm going to put parentheses around here for a reason because people are going to mess it up. All right, 360 divided by twice the number of sides, and that'll get your angle measurement. And in this case, we go 360 divided by 20, 360 divided by 20, and we get 18 degrees. Boom. Okay, so that gives us this little triangle, a little sliver of a triangle that is 18 degrees, and I'm just going to draw that off to the side, and I'm going to find the area of it. Okay, so right now this is my apothem. I'm just going to use an A from now on, and then I would like to use maybe an S for side length right there. But the problem is it's really half a side length, and then also S's look like 5. So I'm just going to use an X right there. The nice thing about using an A there is it can stand for your apothem, and it can also be like A squared in A squared plus B squared equals C squared, and so forth. It can also be, if we're talking about this, 18 degrees, that would be your adjacent side. All of these things start with an A. How nice, how familiar, all right? And our hypotenuse, this would be our radius. So I'm just going to put an R right there. Okay, so we're going to shorten things down a little bit. But from here on out, this is a solvable triangle because we know that X is 4.5. It's half of the side length right there. Okay, so we want to find the area of this triangle, and I believe this stuff over here also requests a radius length. So we would like to solve this triangle essentially. We want to find all lengths associated with it. So let's do a little trig. Label up your sides. This would be our opposing side. This would be our adjacent, nicely already labeled, and this would be our hypotenuse. The thing that is critical to actually solving the problem would be the length of our apothem. So I'm going to write a cosine ratio. So I'm going to say cosine of 18 is our apothem length over, let's do, that won't help us at all, will it? Let's do a tangent ratio. Tangent ratio will be the answer here. Let's go do a tangent of 18. My apologies. We're going to go opposite over adjacent, so that's going to be 4.5 over the length of our apothem. So I'm just going to set up that equation. Again, show your work. If you don't show your work, this is a multi-step problem, and by the time you get done, you've probably made an error, all right? But if you show your work, and I can see that you've made good progress, all will be not perfect, but it'll be good. All right. And then remember, treat this like a cross products problem if you want to solve it. So multiply across the diagonals, or you can just also swap these two positions. So I can say that our apothem length is equal to 4.5 divided by tangent of 18. And we're doing pretty good on that. The only mistakes I saw on our past trig test was the fact that people reciprocated that fraction figuring out a length. Okay. So 4.5 divided by tangent of 18. Remember, you should be able to get a reasonable answer. Our side length is 9. That apothem looks to be considerably longer. So and in fact it is. So that's 13.849er. And I'm going to keep a few more digits running. I'm going to keep recalling my answer. I'm going to go second answer, second recall. Whatever works on your triangle or whatever works on your calculator, just keep a couple more digits than 3 going. 5 is plenty, but 3 to 5 is absolutely minimal, okay? Or actually required, that's the bare minimum, 3. Try to go 5. Or just keep recalling your answer, okay? So we have our apothem length, we have our x length, so we have our base and a heart of a triangle. We could actually, find the area of this polygon at this point. The side problem, the sidebar, does ask for a radius length. So at this point, we can say a squared plus x squared equals r squared. And if we plug all that stuff in, this is the 13.849er squared plus 4.5 squared equals r squared. And solving that, let's see what we get. Second square root of my answer squared. So I'm just on my calculator, I'm just typing in second answer plus 4.5 squared. I'm taking the square root of that. My radius is 14.562. So you could have also used a cosine ratio or a sine ratio to get there, but Pythagorean theorem was staring me in the face at the moment, so I decided to go there. Okay, let's fill out some stuff over here. Central angle. Well, our half central angle is 18 degrees. We figured that out. The central angle would be double that, 36. All right. Side length was given to us at 9 centimeters. Half side length was 4.5. Radius length, we just figured out over there, 14.562. 14.562. And our apothem length, we had to figure out too. That was 13.849. 13.849er. All right, then we're going to go find the area of that little slice. Okay, so we go over here. This is the slice that we want to find the area of. So when it says area of the little triangle, that's what we need. So remember, the area of a triangle is just 1/2 base times height. And the base of our triangle, it depends on which way you want to look at it, but I'm going to look at it the way it was presented to us. I'm going to go 1/2 times 4.5 times our height, which is our apothem, which is 13.849er, and then we'll keep a couple digits there. We'll go 5, 7. Still on the computer screen or calculator screen, so it still works. The area of the triangle is 0.5 times 4.5 times 13.849er 5, 7. Bam. 31.1615. We'll call it. And that would be centimeters squared. We can report that up here. 31.1615. All right. And then it says we only need the area of the polygon. Oh, then you got to go think. Okay. We got a decagon. I just found the littlest slice of 1/2 pizza. How many of these blue scribbled out triangles would it take to completely cover that decagon? Well, you need 2 of these to cover each side. So, and it has 10 sides, so that means we're going to take this times 20. So the area of the decagon, nice to label your work, would be I need 20 of those 31.1615 centimeter squared triangles. So I'm just going to take my answer times 20. Bam. That is 623.230 centimeters squared. There it is. Area of the decagon, done. And you could put it up in the little sidebar there. But that's basically it. Basically, you take the regular polygon, you break it into a right triangle, and you're golden. Okay, so this is another example. This time we have a hexagon. I just want to show you a couple of little things here that might be different. Our goal is here. All right, so we got our little triangle drawn. Then we want that half central angle. So this is a hexagon. So I'm taking 360 divided by twice the number of sides. So that'd be 12. And that would get us a 30-degree angle. Now, hey, that's kind of cool because now this is a 30-degree angle, which means this is a 30, 60, 90 right triangle. So if we really just want to solve the problem, we can say, okay, well, I'm going from long leg to short leg, so I'm going to divide by the square root of 3. 6 divided by the square root of 3, we've got to rationalize that denominator. So I'm going to multiply by a fancy version of 1. One of these jobbies again. Should be pretty used to this, though. 3 over regular 3, that is 2 times the square root of 3 right there. 2 square root of 3. So that can serve as the base of that triangle. And you can get this problem done pretty darn fast. So you can come over here, go area of that little triangle is 1/2 base. We're going to say 2 times the square root of 3 times height, which is 6. Get a decimal for that. Look at that. The 1/2 and the 2 cancel each other out. You're really just taking square root of 3 times 6. if I can type that in. There we go. That is 10.392 for the area of that little guy, and that would be inches squared if we're thinking about labels. That's always good to do. Okay, so that's the area of the triangle. So the area of the hexagon, you come over here and you think, okay, how many of those would it take to cover the entire thing? It would be twice the number of sides, so that'd be 12. So we're going to go 12 times our previous answer, 392. And you can get one of these problems done pretty darn fast if you're a little lucky. Hexagons are nice because you can use those shortcuts. Otherwise, you're using trig, which slows you down a little bit. But all in all, we're at 124.707 inches squared. There we go. Done. All right. That's polygons. And you might say, well, didn't the title of this thing say polygons and circles? It surely did. Flip your page over. And you come up with this problem. And I'm going to change it a little bit. I want to change this not to 1 unit. I want 4 units. And you know what? Let's just give an actual unit. Let's say 4 centimeters. All right, just to keep things real a little bit. Okay, so I'm going to change it from 1 unit to 4 centimeters. All right, and I want to find the area of a regular 5,000 gon. So I stand no chance of drawing that. But if I picture that in my head, that's darn near a circle, I would imagine. Yeah, that would, you think about adding a side and it just keeps getting rounder and rounder, and it's essentially a circle. So this is kind of our bridge to a circle, an area formula for a circle. So essentially, we're finding the area of a circle. We're just going to approximate it with a 5,000 gon. We're putting on our calculus mindset here. So I stand no chance of drawing a 5,000 gon, but I can draw a representative little right triangle geo, right? All right. And we can figure out, let's see, our radius, it said was 4 centimeters. And then our central angle, so I'm going to go 360 divided by 10,000. Now I think in this problem it's going to be very important for us to save our responses. So 360 divided by 10,000, well, that's just going to move the decimal point 4 spots to the left. So that is 0.036 degrees. Very, very, very small angle. And we need to figure out our x and our apothem length. So this works out a lot like one of those velocity vectors that you have to split. So if that's our angle, this would be our opposing side. This would be our adjacent side as labeled. All right, so we can do a sine ratio and a cosine ratio. So I'm going to go sine of very small angle, 0.036, equals our x value over 4. And then to solve this one, all we have to do is multiply by 4 on both sides. All right, that's going to get a horrible, nasty number, but it will be a number nonetheless. So I'm going to go 4 sine of my answer. Why not? I'm just going to grab that answer. That's a very small number, 0.002513. And I'm going to keep all of that. In fact, I'm going to store that in my calculator as like a value. I think I showed you that, but just keep as many digits as you can. Keep them going. 274, ... Okay, so we got a half side length of that. I can also do a cosine ratio of the same angle. And that'll get us our apothem length over 4. And again, to solve this one, we just have to multiply by 4. So we're feeling very repetitive right now. That's fine. All right, so our apothem length is just 4 times the cosine, 4 times cosine of very small angle, 0.036. I'm just making sure I got all my decimals in their correct place. And that is very, very close, but not quite 4. So 399er, how many nines? 6 nines. And then 2, 1, and I'm going to store that value in my calculator as well. Okay, so now that number can serve as the base of my triangle. That number can serve as the height of my number. All right, so that's base, that's height. And so the area of my triangle is 1/2, this 0.002513 jobby times 3.9, a bajillion nines and some change there. Okay, so you get the idea. Punch those numbers in, so 0.5, and I'm just going to go times alpha A times alpha B, and I should get the area of that triangle. It's a very small sliver, remember, so this is a very, very small number. 265, etc. 50265 65469. All right, so that's the area of the triangle. That is one sliver of our 5,000 gon. And in order to fill out the entire 5,000 gon, we would need twice that many of triangles. So what I'm going to do is area of our 5,000 gon is 10,000 times my answer from the previous one. So I'm just going to take that times 10,000, and that's literally just moving the decimal spot over, right? And so we get 50.2654693. And that decimal continues. So all throughout this problem, I have not truncated or rounded my decimal at all. I've recalled my answer every time it was necessary. That means that this decimal approximation of the area of this 5,000 gun is pretty much dead on. Now, there's nothing special about that. Okay, so should a circle with a radius of 4 have an area of 50-ish? Well, circles involve pi a lot. So here's what I'm going to do. Just out of the blue, I'd like to divide this by pi. See what happens. All right, so I'm going to take my answer, again, just using my answer, and I'm going to divide by pi. See what happens. Holy, look at that. That is just, I'm thinking that the reason this answer has such a horrible, nasty number at the end of it is circles have pi in them. Pi is an irrational number. That's probably where that horrible, nasty decimal comes from. So if I divide by pi, I can see what other components are involved. And when I do that, I get 15.999999579. So that means that my answer to the area of that 5,000 gun was really that. And you can see that it's not too far of a stretch to say that that is really just 16 times pi. All right, now why does that matter? Well, is 16 special? It's special compared to what we started with. What did we start with? We started with that. We started with a radius of 4. Well, what's 16 if not 4 squared, which is pi times 4 squared. Interesting. So we approximated the area of a circle using a 5,000 gun, and we got that the area is essentially my radius squared and then a pi in it. That is indeed your area formula for a circle. So area formula for a circle, pi r squared. Put that in your green sheet and keep it. All right. That's it. So you should be able to use that formula right there to figure out the area of any circles. You know, just take, if your radius is 3.5, you just go pi times 3.5, make sure you square it, and you'll be good. Tack on a label. You're dealing with area, so it's always units squared. All right. I want to just preview your homework real quick. If you take a quick look at your 13.2 worksheet, I'm going to ask you to find the area of 3 polygons. Straightforward. Each problem is just a little different. I give you a side length, I give you a radius, and then I give you an apothem. So make sure that you can work all 3 different examples. And then you're going to get some weirder stuff like this. So go find the area of that. All right. They involve a circle and a polygon at the same time. Common question, find the area of a shaded region. So you always think of shaded as positive and white as negative. So in this case, like strategy-wise, think about what you might want to do. We got a circle, and if you subtracted an octagon from it, you get the little slivers around the outside. And that's your day, folks. As usual, there is a partial answer key online, and you can use that as a guide, or if you think you're ready to go, go for it. And there's always a Schoology assignment. Until next time.